Welcome. Today we're going to be looking at the notes worksheet entitled Inverse Trigonometric Functions Day 3. And so this for us would represent the culminating piece of our 3-day section dealing with inverses. It also allows us an opportunity to kind of go back and really look at some of the basic trig functions and derive some more meaning with some of the variables that we've seen. So I think we'll go ahead and dive right in here. There is a review making up most of the front side of your page, and so we'll read a couple things and write some ideas out and hopefully put a lot of what we've developed into some good context here. So here we go. Letter A, it says, what do the inputs and outputs of the 6 trigonometric functions represent? And so there they are, sine through cotangent, all 6 of them. And I guess there's an independent variable and a dependent variable. Independent variable would be our x's, representing our inputs, and the y's, or the dependent variable, would be representing our outputs. So what does each one represent here? So if you kind of think about this, I'm going to write a few things down on the lines on my board, and you guys can paraphrase a little bit if you'd like. But in essence, when we're talking about the independent variable of our trig functions, the inputs really represents the angle measurements. And we do want to be a little careful of this because we're talking about them in terms of our functions. Really, we're talking about those angle measurements in radians. And so what that allows us to do is really take the sine or the cosine or tangent of any real number. Even though officially it is an angle measurement in radians, because the measurement in radians really just represents a real number, it opens up the doors to exactly that piece. So the inputs would really be just any real number. And what that would correspond to, of course, is the angle measurements in radians. All right, now the outputs would be each of the particular ratios. In fact, that's what I'm going to pretty much write in the blank here. So each one is defined differently, so we do have to be careful on that. But every number or every angle measurement, and we're talking about it in radians, has 6 ratios that go with it. So we would be looking at the particular ratio at that angle measure. So, trying to make a long story short here. The inputs for these trig functions would be the angle measurements, and the outputs would be the ratios at that angle measurements. Okay, so inputs and outputs, everybody. Then, of course, what we're going to do is move to part B, and it says, what do the inputs and outputs of the 3 inverse trigonometric functions represent? So we looked at these 3 right here, inverse sine, inverse cosine, and inverse tangent. And I'm hoping everybody would agree with me, based on the way we've developed the concept of inverses, is that the inputs and outputs from a contextual standpoint, they switch. They are interchanged. And so in this particular case, again, this is how I wrote it on my sheet, and you can paraphrase if you'd like, but the ratio would be the input. So I'm going to write it like this on mine, and if you could do the same. The ratio for that defined function. This is how I wrote it. So it's either the sine ratio or the cosine ratio or the tangent ratio, whatever the case may be. It is the ratio, though. And then here's where we have to be a little careful. The outputs represent the angle. And here's where we need to be especially careful. In the restricted interval, everybody, and we'll kind of go over that piece in just a little bit, but in the restricted interval, that produces the ratio. Okay, so again, being the inverses, they switch notions. The input is the ratio, and the output is the angle. Now remember, we've kind of talked about this before, but it certainly bears repeating. When we're talking about our ratios, potentially there are an infinite number of angles that have that particular ratio. But the way a function works is one thing goes in, only one thing can come out. So we've restricted our intervals on those angles to get our single output, our single angle measurement. All right, good. And we'll talk about that as we go through the process. All right, let's go to my next board here. And if you know this stuff, wonderful. Again, it really just, if nothing else, it just reinforces the concepts that we've been developing for some time now. So let's go to part C. And it says, how do we evaluate each of the following expressions, and then what is its value? So if you can tell me what sine of pi over 4 is, that's great. Half the battle. what I would love to do is, again, just derive a little more meaning from that expression. What does it mean when I'm asking for the sine of pi over 4? So here's how I would say it. And again, you can formulate some other ideas as well. But I would ask myself this question right here. So pi over 4 is an angle measurement in radians, or again, just a real number. And I would ask myself, what is the y over r ratio, because that's the sine ratio, everybody, at pi over 4 radians? I guess that's exactly what I would ask myself. So in terms of the sine ratio, that is the vertical component in relation to the direct component. Now, you guys don't have to write this on your paper. I'm just kind of thinking out loud with this. So pi over 4 would look something like that right there. That, again, in degrees, it would be 45 degrees. And, of course, every angle has the 3 components that goes with it. The x, which would be from here to here, the y, which would be from here to here, and the r from here to here. And so no matter where you are on that terminal side of pi over 4, essentially the y to r ratio is going to be a constant. And what we determined through a variety of representations is that y to r ratio at pi over 4 is exactly square root of 2 over 2. And so that's your answer. So I'm hoping the angle measurement makes sense, again, in radians. And then the sine ratio would be the y to r ratio, the vertical over the direct. Okay, perfect. Again, just hopefully you're with me on this and it's starting to click for you. Let's go into the next piece. When I see cosine of negative pi over 6, I would ask myself basically, what is the x to r ratio? So cosine is one of the 6 ratios for every angle measurement. So what is the x to r ratio at negative pi over 6 radians? Perfect. And so I would kind of go right over here, and let's sketch this out. Negative pi over 6 would probably look something like this, give or take. And so remember, this angle, of course, has an x, it has a y, and it has the r. Just trying to formulate that on your paper for you. And then in this particular case, I would be looking for the x over r ratio for any point on the terminal side of that angle. And the x to r ratio would be exactly square root of 3 divided by 2. And so the cosine of negative pi over 6 is root 3 over 2. Last one, everybody. On this set, at least, if I'm asking for the tangent of 0, here's what I would ask myself. What is the y over x ratio? So tangent is one of the 6, and it would be the ratio of y to x for any angle at 0 radians for here. So that's what I would ask myself. And again, I'll just kind of come over and sketch this out, maybe get a visual understanding of this, even though we've developed this before. There, of course, everybody is 0 radians. And as I kind of pick a point on that terminal side there, if I was to take the y-coordinate and divide by the x-coordinate, well, of course, as we can see, guys, the y-coordinate is 0 right there. And so if I take the y-coordinate and divide it by the x-coordinate, I should, of course, get 0. All right. So each angle has 6 ratios that go with it. Here are your 3 primary ones. The secondary ones would, of course, be the reciprocals, but that's pretty much what we're asking. Okay, so that is part C, and we've been working on that for a long time now, so the hope is that's clicking nicely. All righty. Now let's go into part D and rehash a couple of things we've been doing the last couple of lessons and working with the inverses. So part D. How do we evaluate each of the following expressions, and what is its value? So here's where we want to be careful. Inverse sine of 1/2. Remember, everyone, this is the sine ratio. The output is the angle. So here's what I would kind of ask myself. What angle? Now, because there are an infinite number of angles that have a sine ratio of 1/2, I need to be specific about the interval. And so I'm going to do this for right now. We're going to be a little clearer a little later on. But for sine, if you remember, the restricted interval is from negative pi over 2 to pi over 2. So what angle between negative pi over 2 and pi over 2 has a y over r ratio? That's what sine ratio is, of course. Has a y over r ratio of 1/2, 1 over 2. That's pretty much what I'm asking when I see that expression right there. And so then I go to my coordinate plane and kind of think things through. Here would be rotating down to negative pi over 2. Here would be rotating up to positive pi over 2. Somewhere, either rotating this way or this way, there is a sine ratio of 1/2. And what we determined, of course, is sine ratios are positive up here, not down there. And so I would be looking for a y to r ratio of 1/2, something like that. And what angle has that, of course? Well, we've seen it as pi over 6. And so the inverse sine of 1/2, everybody, is pi over 6. Good. We're doing great. Let's keep it up here. So 2 more on this end, and then we'll draw a couple things out and do some examples with this. So here we go, everyone. Inverse cosine of 0. Now, again, we have to be a little careful. Cosine is the anomaly here compared to the other two. So the interval for cosine is different than the interval for sine and tangent. So if you remember, in this case, the way we formulated it has to be in between 0 and pi. So what angle between 0 and pi has an x to r ratio of 0? That is exactly what I would be looking for right there. And so if we kind of take a look at it, I'm going to have to go down here. So remember, cosine would be going from 0 to pi. So that's from there to there. Cosine ratio of 0, that's an x value of 0 on the unit circle. That would be right there. And so what would be that angle, of course? It looks to be pi over 2 in this case. So here's my angle, and I would be looking at it at pi over 2. So inverse cosine of 0, everybody, is pi over 2. That's the angle in that interval with the cosine ratio of 0. One more here. Let's go for it. Inverse tangent of -√3. So here's what I would ask myself. What angle, and from negative pi over 2 to pi over 2, so what angle there, the restricted interval for tangent is exactly that, has a y over x ratio of -√3/3. That's the question that we would ask ourselves looking at that piece. Oops, I'm sorry, I have that wrong. Let's quickly change that for you, because it's -√3. There we go, a little better. Perfect. And so I would go ahead and think about it in terms of the coordinate plane there, and we'll draw a little circle a little later on, but essentially from negative pi over 2 to pi over 2, so either rotating up to get the positives or rotating clockwise to get the negatives, and I think we're going to be down here. But basically we would probably see something like this. The y to x would be -√3. Should look something like that. And what would be that angle, of course? I mean, we kind of know these angles going through. Rotating clockwise downward there, I'm seeing it as a -pi over 3. Okay, so again, I hope just the review helps really reinforce some ideas that we've been developing for a while now, and especially the inverses. I know they can be especially tricky. So hopefully that puts it in a little bit better perspective for you. Please, again, at any point, just let me know if you have some questions, and if I can elaborate or clarify on anything, you let me know. Okay, otherwise I'm going to go to my next board right there. And this is good, just a little true-false type stuff, just a yes or a no, I suppose. And I guess the best thing to do for this review problem, and I'm hoping you have a little room on here, is let's go ahead and do 3 circles, one for inverse sine, one for inverse cosine, and one for inverse tangent. This will allow us an opportunity to just put it all in one spot. So here's what I'm going to do, and again, guys, you can follow suit or not. That's totally up to you. But I'm going to go ahead and draw something like this for inverse sine. And I'm just kind of thinking, remember the interval for inverse sine is from negative pi over 2 to pi over 2. So I'm going to draw kind of that diagram before, going down to negative pi over 2, or going upward to pi over 2. And again, just some of our special angles that we've been working on, just something like that. That would be the diagram that I would envision when working with inverse sine. Okay, inverse cosine, of course, everybody, is slightly different. And again, I'll leave this up to you if you want to go ahead and draw this in. I would maybe do something like this, though. Separate those quadrants out. If you remember, for inverse cosine, it's from 0, just going counterclockwise, right to pi. So that's what my diagram would look like, so to speak, and I'll throw in my 3 terminal sides in the first quadrant. And remember, cosine's positive in the first, and then it turns negative in the second. So something like that. So I like that diagram for inverse cosine. And then inverse tangent, let's go ahead and get one last circle taken care of here. This one's going to look something like this, very similar to sine, as I have alluded to. So either coming upward or downward from the initial spot. Positive tangent ratios up in the first quadrant there, of course. Negative tangent ratios down in the fourth quadrant. And so from negative pi over 2 to pi over 2, you cover the infinite amount of tangent ratios out there. Okay, something like that would do. And now I think we can answer some of these questions. So let's start it out. And again, if you kind of know these, if you really can work with them easily, great. That's really wonderful. So here's what I guess I would say. Can the inverse sine of root 3 over 2, is that equal to pi over 3? So I guess the first thing we have to ask ourselves, like we kind of did on the previous notes worksheet, is pi over 3 in the proper interval? And sure, yeah, pi over 3 is right here. Here's the terminal side for pi over 3. Will I get a sine ratio of root 3 over 2 right up here, everybody? Sure. And so the answer is yes. And as a matter of fact, that is the case. Inverse sine of root 3 over 2 is pi over 3. Okay, let's go to my second one, which actually will lead to the second diagram. Inverse cosine of root 3 over 2, is that equal to pi over 6? Well, let's check it out, everyone. Pi over 6 is this terminal side right here. Is that in our interval for cosine? Absolutely. And so it's possible, and then we guess we'd go a little further. Does pi over 6 have a cosine ratio of root 3 over 2? Do these two go together with cosine? Sure. They definitely do. And so that's a yes. Inverse cosine of root 3 over 2 must be pi over 6. Okay, now let's stay in that second diagram, but let's go to part C. Inverse cosine of root 2 over 2, is that equal to negative pi over 4? Well, everybody, negative pi over 4 would be down here, rotating clockwise. Is negative pi over 4 in the interval for cosine? No, absolutely not. So the way cosine is defined is from here to here, and obviously negative pi over 4 is outside that interval. So as a result, right away, it's a no. So here's what's interesting and difficult to kind of deal with. If I gave you this, and I wouldn't write this on the paper lest we confuse ourselves, but if I gave you that, what is the cosine ratio of negative pi over 4? You would tell me root 2 over 2. But the problem, of course, is I cannot reverse those and apply the inverse, because out of the infinite number of angles that have a cosine ratio of root 2 over 2, this being one of them, this is not in the proper interval. And as a matter of fact, if you wanted to know the correct answer here, this would be positive pi over 4. So you would have an x over r ratio, a cosine ratio of root 2 over 2. Look up here, everybody. There's the one, pi over 4. That is the one in our interval that has the exact same cosine ratio. So again, I would almost sort of get rid of this piece. Even though that is a true statement, letter C is still not true. All right, letter D. Inverse sine of negative root 2 over 2, is that equal to 3 pi over 4? Well, a couple things I see with this one. First and foremost, here's 3 pi over 4 out here. Is it in the interval for sine? No, absolutely not. And even still, again, I'm just kind of thinking out loud with this. The answer is certainly no. First and foremost, if I even did this, sine of 3 pi over 4, well, guys, this is the second quadrant angle. What do we know about sine in the second quadrant? Well, sine in the second quadrant, it's not even negative. It's root 2 over 2. So again, it's wrong for so many reasons. But the number one thing, as soon as you see it's obviously not an angle in our interval, we would say no regardless. And even still, sorry about that. Projector shut down for a second, but it's back up and running, and we'll just continue. So let's do part E then as a result. So here we go. Inverse cosine of negative root 2 over 2. Is it possible for that to equal 3 pi over 4? Well, if I look at my little cosine diagram here, here's 3 pi over 4. And is this angle in our interval? Sure. Would I get a cosine ratio of negative root 2 over 2? Yes. And so the answer definitely would be yes on that one. Wonderful. So it's in the interval, and it has that ratio. Let's keep going. Inverse sine of 1, everybody. Is that equal to pi over 2? Let's come over to the sine diagram, of course. Here's pi over 2, and that is definitely part of our interval for sine, all the way up to and including pi over 2. Would I get a sine ratio of positive 1 up here for this particular angle? Yeah. And so as a result, this one's a yes. Okay, a couple more here. So inverse cosine of 0, is it possible for that to be 3 pi over 2? Hey guys, 3 pi over 2 would be right down here in terms of its terminal side. And is that in our interval? No, no. So absolutely not. I mean, in this case, though, if I took the cosine of 3 pi over 2, I would get 0, but it does not apply on the inverse because it's outside our interval. Okay, let's keep going. Letter H. Inverse cosine of 1. Can that be 0? Well, let's take a look, everybody. Here's 0 as the angle measure. So it's in our interval, because our interval is from 0 to pi. And everybody, do I get a cosine ratio of positive 1 out here? Sure, I absolutely do. And so there we go. And in letter I, one more there. I see a lot of students have troubles with this one. This is probably one that comes up more often than not. Inverse cosine of 1/2, can that be equal to negative pi over 3? If you know your diagrams, you have a shot, everybody, because here's negative pi over 3 down here. That's where the terminal side would hit, and that is definitely outside our interval, and so as a result, the answer would be no. So if we were to actually do the inverse cosine of 1/2, we would want the angle that has the same cosine ratio as this, but in the interval, and that would be pi over 3, by the way. Inverse cosine of 1/2 is pi over 3. Again, just hope that helps putting some things in perspective a little bit, especially the review problems there. All right, and there's one more type of problem to take a look at. It's another composition issue, but we will not be undoing the operation. So the other day we saw like sine and inverse sine, something like that, and they would theoretically, potentially cancel each other out. That's not how this works right here. And again, these are fairly contrived expressions, but I like them because it really reinforces what each part means. So what does the inverse tangent of 3/4 mean? And then what does it mean to take the sine of that angle? So I'm looking at example 2a and sort of trying to piece that together. So we'll write a few things in. I guess the one thing I would recommend for all of these problems that you do, please use a diagram. You'll see me use it, and I would encourage you to use one as well. So this is what's called a composition expression, really taking one trig function and applying it with the inverse of another trig function. So let's try it out. So here's how it's going to play out, everybody. If you would, let's, for part A, draw a coordinate plane. And let's try to derive a little meaning from this as well. I would go from the inside out. And so I'm going to just try to figure out what the heck this means and then see if I can draw a picture of it. When I ask for this, I'm asking for the inverse tangent of 3/4. What I'm really looking for, of course, this is the tangent ratio. And so when I take the inverse tangent, I'm looking for the angle. And of course, for tangent, it's between negative pi over 2 and pi over 2. So the angle between those two values that has a y over x ratio, because that's tangent, of course, of 3/4. That's pretty much what we're after. Now, we don't know what that is. By the way, for this problem, we don't necessarily need to know what that is. But that's pretty much what that expression is asking. And so I guess I would start to formulate some ideas with my coordinate plane and figure out that it has to be in between negative pi over 2 and pi over 2, so either in the 4th quadrant or the 1st quadrant. And as we all know, tangent is positive up in the 1st quadrant, so I'm going to draw my terminal side up there. And because we're talking about a tangent ratio of 3/4, we're talking about a y over x ratio. So this would be 3 for every 4 that x value is. Perfect. And again, this would be my angle right in here, just FYI. Not that we even need it, but I'm going to sketch that in. Okay, that's the first part. Now, everybody, we go to the second piece. and we're looking for the sine ratio of that angle. So that's exactly what I'm going to do here. I'm going to write it as the sine ratio, or really the y over r ratio. Let's see if I can get that in for you. So the sine, or the y over r ratio, at this angle, whatever it may be. Okay, so we use the ratio to produce the angle. Now we're going to use the angle to produce the next ratio. And so when I look at this, if I'm looking for the sine ratio here, everybody, it's y to r. And the only thing that's missing, everybody, of course, is the r. And I'm hoping you all realize it's a 3, 4, 5 triangle. 3 squared and 4 squared would make our 5 squared. And now, everybody, I've got my y over r ratio. It's 3 to 5. And so you would find, of course, the sine of the inverse tangent of 3/4 is 3/5. Let's go ahead and just try that out. So, of course, I'm going to ask you to do these without a calculator. In fact, I'm thinking on the next assessment, there definitely is a non-calculator part, and I could envision these types of expressions being on there. So sine inverse tangent 3 divided by 4. Close it off there, and there we go. 0.6, 3/5. Nice. Let's go ahead and try to find part B. Let's do that one together. So, same situation. I'm going to draw a couple arrows here just to figure out what the heck I'm looking at, and then from there draw it out and go. So I guess when I see part B, inverse sine. So when I see inverse sine of -1/3, I'm asking for the angle between -pi/2 and pi/2 that has a y over r ratio, because that's sine, so y over r ratio of -1/3. All right, that's what that inside expression would tell me, and let's play it out, of course, perfect/ly up here on the coordinate plane. It's so easy to do when you see it, and so hard to do when you don't. So let's see, so from -pi/2 to pi/2, because we're talking about sine here, so I'm either going to rotate downward, where sine is negative, or upward, where sine is positive. And in this case, as you can see, we probably want to rotate down clockwise there, probably be in that vicinity. And this would be a y to r ratio of -1/3. Of course, as we all know, r is always positive. And because I'm going down, the y value is negative. So that's what this diagram would look like at this point in time. And so now I've drawn that in. This would give me the angle if I applied this piece. Now this part just asks for the cotangent ratio at that angle. So let's write exactly that. So cotangent ratio, and remember cotangent, everybody, is x over y at this angle. And so as you can see, everybody, we're probably going to need that x value right here. Everybody, a little Pythagorean theorem would do well here. And I'll just write it as x squared and -1 squared equals 3 squared, just in case you have some issues with that. I am seeing x squared equals 8. And so x equals square root of 8. If it's okay with you guys, I'm going to go ahead and put this as a 2√2. Now we've said it before, certainly bears repeating here. Be very careful with positive versus negative. My angle is in quadrant 4, and so my horizontal component here is positive. So x is equal to 2√2. And so just, again, be a little careful on that piece. And so as a result, could I get that x over y value? Yeah, it looks to be 2√2 over -1. And just -2√2 if we have that. And that's it. That's how it's going to play out. So you can see how these compositions work out pretty well. I think these are actually a little even more straightforward than the ones we saw yesterday, with the undoing and then is it in the interval, is it not. These, I think the definitions really take hold nicely, and you just draw it out, label, and you have the background to be successful with this. Okay, let's maybe do the last two. So sine inverse cosine of -1/2. If you're understanding what's going on here, that's fine. You don't have to write in all my stuff. I'm just trying to cover my bases. So when I see inverse cosine of -1/2, I'm looking for the angle between 0 and pi. Okay, so just be careful with that. that produces an x to r ratio. So cosine ratio, so x to r ratio of -1/2. That's exactly what I would be after. And so I come over here, of course. Here's my coordinate plane. And let's kind of figure out what's going on in this case. So 0 to pi for the interval on cosine. Cosine's positive in quadrant 1 and negative in quadrant 2. So all of my cosine ratios are covered from here to here. -1/2 cosine ratio, something like that, give or take. And so the x to r, x would be negative, r, of course, would be positive. That's what it would look like. Okay, good. And I'll include, in fact, the rotation there, just kind of looking at that piece. There's my theta. And now, of course, everybody, what am I looking for this? So now I'm just going to apply the sine ratio. When I'm talking sine, I'm talking y to r at this angle. This should look familiar, by the way. This is one of our special ratios and special angles that produce them. If you do a little Pythagorean theorem here, you would get square root of 3, by the way. And again, positive because I'm going up. Just be careful, positive versus negative. Direction matters. And there's the y to the r, and that would be √3/2. Perfect. Now, as I said, you kind of know this angle already. So when I see this, and you don't have to write any of this down on your paper, this actually is something we know. If I gave this to you on a test, you would be able to figure it out. That actually is, I'm going to just work over here, 2 pi over 3. The inverse cosine of -1/2 is 2 pi over 3. It's the angle in the second quadrant that has that special cosine ratio, excuse me. Then, of course, what I would be doing is taking the sine of 2 pi over 3, and we know the sine of 2 pi over 3 from the unit circle and some others. It's √3/2, and there's your final answer. So again, it just matches up pretty much with what we already know. In this case, the special angles worked out nicely. Last one, everybody. Tangent inverse cosine of square root of 3. Let's take a look at this piece right here. And so 0 to pi for inverse cosine. And let's see, x to r. So I'm getting an x to r ratio of √3, so it's got to be positive. So I'm just going to draw a first angle quadrant there. So this would be √3. This would be +1. And then watch what happens here, by the way. Of course, we would find that angle, and then we would take the tangent ratio for this angle. And, let's take a look. I would do √3 squared plus y squared equals 1 squared. And notice what you end up getting, by the way, when I solve this algebraically. I end up getting the 1 squared minus √3 squared. I end up getting this. And, hey, guys, is that possible? No. I'm not sure if you saw this already, but is it possible to actually have an angle with a cosine ratio equal to the square root of 3? And by the way, everyone, square root of 3 is about 1.73-ish, somewhere in there. Can we ever have a cosine ratio above 1? No, of course not. And so you can see it just kind of bared out mathematically. If you figured that out right away, that's great. That's great. But now that simply does not work. And so as a result, that's not something we can do. Okay, I'm just going to pick up the calculator real fast and just show you that piece. But I think we're pretty much all set here. So tangent inverse cosine, square root 3, close, and no luck, of course. Good. So obviously, guys, we tried to draw it out. I mean, that would be my first step if I didn't understand that piece. But it just didn't play out mathematically. All right, well, I hope this lesson kind of brought some things back into perspective a little bit and helped you out with understanding the concept of an inverse. Obviously, if there are any questions at all, you'll let me know about them. Please try the independent work, and that's great. Thanks, of course, for listening.